Okay, so Harm is our local son, favorite son. Gone off and made big out in the real world. Actually, he's really from the Netherlands. He's Dutch. He came here as a postdoc, so many years ago. He was here for a while. He did all kinds of great things. We've heard about them. I'm just really excited to have him come back. Tell us about it. He always thinks of new, weird things. This guy's a very creative mind, in my opinion. And I'm just really happy to have him back talking with everybody at tea time. So, take it away, Harm.
All right, thank you. Very nice introduction. Yeah, it's great to be back. It's been about 3 years. See a lot of familiar faces still. Maybe they now work for different companies, but they're all still in the same ecosystem, which is great. Yeah, so today, what I like to do, what I want to use my time for, is really have a discussion with you guys about the discount factor, because there is a lot of, it's one of these things that everybody or most people know about. Everybody in RL knows about it, but there is some, if you look a little bit closer, there is a couple of subtle things that I want to talk about. So I really want to start this talk with a couple of questions. So who can tell me what the discount factor is? Let's start off easy. Yes, Rich.
Oh no, you just said
yeah, it's sort of.
You don't have to tell me.
Yeah. So okay. It's 2 questions. Who does not know what a discount factor is? Okay, a few people. Okay, who does know what a discount factor is? Which is the rest. So I can ask anybody I want to explain what the discount factor is. Correct. Maybe you want to briefly explain.
The discount factor says how much we care about future rewards. It allows us to say we don't care that much about them, or we care about as much about them as we do about the current next step.
Yeah, that's perfect. So it's really, it controls how much you care about future reward versus your current reward. So it's an important parameter, but when we play with that parameter, it's usually always, we only test a certain range. So I want to ask a different question, which is, suppose that you're working with a sparse reward domain, you're doing function approximation. What would be a good gamma value? Should I set it? What's a good value for setting your gamma value? I'm not going to ask Rich this time. I'm going to ask somebody else who can tell me. You're working sparse reward problem, function approximation. Can you give me some ideas on how to set my gamma? Yes, in the back, Dale. You set it to 1. Well, that's an interesting choice. So that might work in some tasks, but I'm gonna bet it's not gonna work very well in most tasks. So there are issues with that. But okay, let's do it slightly different. Who would say you should set the gamma value high?
0.9. It's always 0.9.
We have a 0.9. Who tell? Okay. So it depends on how far your goal state. So you're thinking into. Okay, so if it's a large state space, you should set the discount factor a high value. Okay, but if it's large, should you set it high or should you set it low? Okay, I'm gonna restrict to 3 options. I'm gonna ask all of you. Who tells me it should be high? Just raise your hand. Who thinks it should be high? All right, that's a fair amount. Who thinks you should set it low? I see 1 person. Why do you think we should set it low?
We should use all the games.
We should use all the gammas. Okay, that's even a third option. So all the gammas who thinks, okay, that's a special case. I think most people wouldn't agree. Well, most people would not choose that option, perhaps.
How many think it should be 0.9?
It's a good question as well. So 0.9, go with 0.9. That's also an option. Third option is it depends. It depends on your problem. I think that I'm going to summarize Janie's choice to that choice. So it depends on the task.
It also depends on your function approximation.
Okay.
It might not like high values of gamma.
It might not like high values of gamma. Okay. All right. Okay. So we have a sort of a consensus around high gammas. You should set it, give it a high value. And so, yeah, so the goal of this talk is really to get that percentage down that voted for high gammas. And so I'm going to ask the same question again at the end, and that's my measure of success for my talk, if I can get that percentage down. And so, yeah, so I want to go into a little bit more detail about the discount factor. And so, like the first thing to realize is that whole question of what is the best discount factor, it has an implicit premise, which is that you measure the performance by something else. You have a measure that is independent of the discount factor, because otherwise it doesn't make any sense. So, and this is, I want to argue, very often the case that the way you evaluate your agent is different from what the objective that you give your agent. So what I want to do now is sort of introduce a few definitions such that we have a language to talk about it more easily, and then I'm going to say a few things about it. So I'm just going to start off very basic with stuff that's very familiar, maybe slight variation to what you're used to. So I'm going to define an MVPM as a set of states, a set of actions, transition function and a reward function, and an initial state distribution. So note that gamma is not part of my definition here. So a policy, in a general case, is just a sequence of an experience sequence from your very first state to your current state. So states, action, rewards, and it maps to a distribution over actions. A stationary policy is a special case of the more general policy, which means that your policy only depends on your current state ST. And a non-stationary policy basically is all the other cases. Now, I'm going to define a performance metric, which is the way you evaluate your agent, which can be all kinds of different ways, but ultimately it's a function that takes as input a policy and outputs a single value. And I'm going to define a task as the combination between an MDP and a performance metric. And I define my optimum policy as a policy that is optimal with respect to this performance metric. Now, to contrast, by contrast, I have also a learning method, which I'm going to call FL, which is a similar type of function. It takes as input a policy, output a reward, output a value that gives it a score, how well it does on this metric. And we're going to call the policy that optimized, that's the best according to this metric, my optimal learning policy, pi L star. Well, of course, because those metrics in the general case can be different from each other, also those policies can be different. So the optimal learning metric is not, optimal learning policy is not necessarily optimal with respect to F. So I'm going to define the difference in performance between these two policies. I'm going to define that as a metric gap. And so it's the performance of the optimal policy according to F minus the performance of the learning the optimal learning policy according to F. And so we're going to have a look at this. Yes?
Sorry, the performance metric doesn't depend on the MDP? So
yeah, it depends on the MDP.
You evaluate this regardless of what MDP we have?
No, it should have a subscript M. I just keep it very simple here. But yeah, it depends on the MDP.
So
because it evaluates always with respect to an MVP. More generally, yeah, sorry.
Oh. So the MVP is in the performance metric. So what does the task add to it? So I mean, it takes the task is the performance metric that already has the MVP in it and adds the MVP on it. So what does it add?
So it's just you have an MDP and you have a performance metric over that MDP that evaluates any policy for that MDP. It gives us a certain value. I sort of use simplified notation here a little bit, just to sort of keep it nice and not too many subscripts. But it's not hard to think about the more like how it would, you know, the dependencies. It's a pretty straightforward case. There's no hidden. I'm not doing anything anything hidden or something. Try to push something away. It's very simple case. So okay, so we have these two metrics. We have the performance metrics. We have the learning metric. Now, the particular setting that I'm going to focus on is the setting where our performance metric is an finite horizon undiscounted metric, whereas a learning metric is a infinite horizon discounted metric. So we have for the learning metric we have as a hyperparameter we have gamma, and for our performance metric we have h, our horizon. Now I just want to motivate this slightly why this particular setup. The reason is that this is a very common scenario. For example, if you evaluate DQN on an Atari game, this would be the scenario that best describes your setting, because what is reported is the total score. It's the undiscounted score, so it's an undiscounted setting. On top of that, like any practical experiment has to stop at some point, so there's always a finite horizon. So in DQN, the Nature paper, they had a 5-minute time limit. So it's really, and then they stop evaluation. So there is a practical argument. There's also a sort of more conceptual argument that, like, really an undiscounted performance metric is not, it's probably not what you really care about, how you really want to evaluate things, because it doesn't make any distinctions between how long it takes to get certain reward. And so in the extreme case, it could take, you know, millions of years before it gets, say you have a game where there is a single reward, it could take 1 million years versus another policy goes in a beeline for the reward. You probably don't want to give these two policies the same score. Now, but it is sort of practical to say, okay, if they, you know, in sort of within this time limit, if it gets this reward, you know, then I'm going to consider them equal. So there is a conceptual argument as well, but the main argument is really like this is how it often happens in practice. So I want to have a look now at how the discount vector affects the metro gap, and we're just going to have a look at a few tasks. So I'm going to start very simple, or all of them are simple actually, but so this is just a navigation task. So you have two objects: a positive object, which is green, a negative object, which is red. You can, and we have an agent that can eat those objects, and the starting position of that agent is the blue diamond. So we have a reward. The green object is +5 reward. The red object has -1 reward. So now we can have a look at, okay, how, if we, under these settings that I outlined, what's the metro gap? So the metro gap, so this is the performance of the optimal policies. So this is the optimal learning policy, and I plotted it as function of gamma because that's a hyperparameter. For the performance metric, I just used a fixed horizon of 12 for all these tasks. So it's just a fixed horizon, so there's no hyperparameter. Well, it's a fixed hyperparameter. And so the red line shows the performance of the learning, the optimal learning policy, and the dotted black line shows the performance of the optimal policy. And so the difference between these two is the metro gap. So what you can see here is for high gammas, for high discount factors, the metro gap is 0, where if you set it too low, the metro gap becomes, well, 4 here. And the reason is that if you know, it needs to overcome this negative reward. So if it has a very low discount factor, it gives a low weight to that final reward, so it doesn't become worth it anymore to eat that red reward. Versus if you set your discount factor high, you give high value to future rewards that are farther away. So in that case, you can overcome the obstacle here and actually get that reward, which is what the optimal policy would do according to the undiscounted metric. So that is one example. Now here's a different example. Now I have two positive rewards. One a small one on the left side plus one big one on the right side, that is plus 5. Again, yeah, so the horizon is 12, and now I can explain why I set 12. So 12 is sort of at the cutoff point that, well, it can get all these rewards in two ways. It can first pick the small one and then the big one, or it can do the other way around. And obviously this one is shorter than this one. So the one takes more time than the other, and the 12 is just a cutoff value that it can, or it's somewhere in between, that if it chooses the long route, then, it doesn't have time anymore to go to the small one. So according to your performance metric, you don't count it anymore. So if you do the same thing again, then you see sort of the opposite. Now the small discount factor has the action gap of 0, whereas the high discount factor, it gets the high reward, that's a value of 5, but it can't get any more to the small reward. So because it took, in a sense, it took I don't want to say the wrong route, because it's okay according to its metric, but it's wrong with respect to f. It's not fast enough. Now, just to give one more example. This is a little bit more complex to show that you can have different cases. So here, the arrows just means there's sort of a wind blowing in that direction. So if it takes a step, if it takes any action, there's a 40% chance that you take a step to the left, which means it has to now trade off the risk of falling into the big negative reward versus that small positive reward. And it's safer to make a very big way around. Versus if you would just walk around here and there's this 40% chance, there's a high chance that you get that negative reward. So if you look at expected values, that's not always the best. And sort of, if you look at now at the same graph again, now first of all, the optimal policy is a non-stationary policy in this case. So you can never get that action gap to 0, because the optimal learning policy is stationary because we use a infinite horizon metric, so it can never get that metric gap to 0. But also you see, okay, the best one is somewhere in the middle. Okay, so that was sort of just that was when we look at the metric gap. Now, obviously, the metric gap is not the only thing to care about. So the metric gap sort of tells you, okay, in the best possible case, this is what my performance could be, given sort of what I tell the agent that should optimize for versus what I really care about. Yes.
What is the learning algorithm that you use?
So there is no learning. It doesn't matter because I look at optimal values. So I analytically computed the optimal values. So any method, like it's just optimal. It's a method independent. It's just the optimal value. Yes.
So these objects are kind of gone from the cell after the agent visits that cell.
That's right.
So how's the state represented? Is the state, different when one of the objects disappears?
So I used a tabular representation, and all that matters here is that it's also independent. Like this is not, because I use a tabular method, like this is not going to change for different representation. There is only one like the state obviously takes into account whether those objects are still present. However you want to encode that doesn't matter. This is always the same graph. Okay, so now we had a look at the metric gap. Obviously, it's not the only thing that matters, and that's sort of to the what you mentioned about the learning method. I didn't use any learning method here. Now we're going to look at a learning method, at least a learning update. So the other thing is that the discount factor affects the optimization process itself. So let's have a look at that. Again, I like simple examples because then you can actually understand something. So this is again a very simple example. just a chain of states. There's 50 states in total. There is a terminal states on both ends. One leads to a value of 1. One leads to a value of -1. Super simple. Clearly optimal policy here. So, oh yeah, and it's a stochastic environment with 25% chance you take the opposite actions from the action that you wanted to take. Optimal policy is very obvious. Always go in that direction. Okay, so now, oh yeah, the other thing to mention here, from the point of view of a metro gap, it doesn't matter what you set your gamma, it doesn't matter what you set your h, action gap is always 0. So there's no performance, so there's no advantage from a discount factor perspective with regards to the metro gap, because yeah, it's always the same. The metro gap, the metric gap is always 0. So it's a good example to focus on other effects. So now, what I did is I used linear function approximation with tile coding. We all are familiar with it, and I changed the tile width. So the tile width can consist of a number of states next to each other. The other thing I made sure of that I use enough tiling such that the true value function can always be represented. Okay, have we 5 minutes left? All right. I guess I have to speed up a little bit. So now, this is what. So, and the other thing, final thing I should mention is I just did update sweeps across the state space because I didn't want exploration to have any effect on this. So, okay. So what you see here is early performance. So I looked here at the first 100 update sweeps, and here at the final performance after many update sweeps. I can assure you it didn't improve anymore. So what you can see here is a couple of interesting things. So first of all, for a tile width of 1, that sort of reduces the method to the tabular method. Then you get perfect performance across all discount factors. As soon as you introduce a little bit of function approximation, performance drops very quickly, and especially so it's only the high discount factors that now work well. Even more, if you make the tiles wider, the effect becomes worse. So it drops off earlier. So you can see it here, for example. You know, the performance falls flat much earlier than if it is a little bit smaller. Like I could go on, but performance went to 0. So this is very strange if you think about it. I used really the most simple settings, just standard linear methods, nothing special, and now you have this performance. So, and we know it's not the metro gap, so it's an optimization effect. We also know it has to do with function approximation, because in the tabular case, it doesn't exist. So what can this be? Sorry? So I used the Q-learning update rule, but I did sweeps across the state space. So one sweep consisted of updating every state action pair. So it's not a full algorithm yet. It's just the update rule, the Q-learning update rule. Not Sarsa Lambda, no. But just, yeah, I want to, yeah. So we all know there is no convergence guarantee for Q-learning in linear function approximation. I'm going to argue that that's not the issue here. And I'll I have some reasons as to why I think that, but I don't want to focus on that right now. So we have this weird thing going on. So, and this is now it becomes interesting because we've shown that there are tasks for which you really want to use small discount factor because the metro gap is smaller, so the theoretically best performance you can get is higher. But now we have this effect as well, which shows as soon as you go to function approximation, those small discount factors don't work. So why don't they work? That's the question. So there is a lot of reasoning about this, why performance for low discount factor doesn't work, and that also, like most theories, involve some around the action gap somehow. They involve the action gap. So the action gap of a state S simply means it's the Q star value of your best action minus the Q star value of your second best action, and so. I just want to mention like 2 hypotheses that you sometimes hear. So I'm just going to name them here. So one is that lower discount factors result in poor performance because they result in smaller action gaps. are lower discount factors result in poor performance because they result in smaller relative action gaps. And by relative action gap, I just mean the action gap divided by the state value. Now, these are two common hypotheses. They are, if you sort of plot those things for different gamma, you'll see that both of them are validated by that one experiment I just showed. So I have to perform different experiments, and it's very, it's very easy to sort of check for those hypotheses, because what you can do here, if you multiply the reward by 100, you increase your action gap. So that if I do that, it should result in better performance for smaller discount factors. This one you can test by sort of pushing up all your values, say by 100, because that would decrease your relative action gap and would result in poorer performance. So, as a good empirical scientist, I performed those experiments, and the conclusion is, well, it doesn't make any difference. So this sort of shows that those hypotheses, something else is going on. And so then we came up with a new hypothesis, which is the following one that I'm also want to test. And the new hypothesis is that lower discount factors result in poor performance because they result in larger size differences in the action gaps across the state space. So what I mean is that in some parts of the state space, the action gap is really high, and then sometimes it's very low. So it's not the problem is not so much that it's low, it's that size difference that's the issue when you're dealing with function approximation. So I just want to define a metric to sort of more easily, I want to get a single number for how hard this problem is. And so I define the action gap deviation, which is the standard deviation of a random variable, where that random variable draws an arbitrary state uniformly at random, and then outputs the log of the action gap. So this sort of, I could also remove the log and then it would seem simpler, but it's really the differences we're talking about are huge. So to make any sensible, to get a sensible metric, I introduced the log. And so just to show you that for the experiments that I just showed, this is how the k plus as function of the gamma for that chain task. So it's indeed, it goes up for smaller discount factors, and like a difference of 1 is huge. That because we're talking about the logarithmic, values. So yeah, so we see now that okay, this hypothesis also is supported by that one experiment that we want to reason about. But now, just like the other ones, we want to sort of change the experiment to see correlation is not causation. We want to differentiate these two. This just shows correlation with the current experiment. Now we want to do a new experiment to test, is it actually, does it cause the problem or is it just correlated with the problem? And so that's a lot harder problem to actually do. And sort of the whole, most of the work was around constructing a method that could bring this down. And the way to do that is, this resulted in the method logarithmic Q-learning. And I don't want to say too much about it actually, because I think just for time reasons, there is actually the archive paper on this work should be up any moment now. It should be up tonight. Like I've submitted it already. It's just a matter of they have to publish it. So you can read up on the method in detail tonight, I guess. Of course, you're all going to do that. But so I just want to point out a few things that are good to know. So what it does is it performs, this is the regular Q-learning update, except there is these weird functions, which the function f, which I call the mapping function, which is a logarithmic function. This is just the inverse of that function. So what you're doing is you're doing your averaging in the log space instead of in the regular space. That's the main thing. And if you look at what it does for the values, so this is the state value. This is the sort of the difference. So it's the action gap across your state space. So we have 100 states in total. This is in the regular space. This is in the log space. Now what you immediately see is that where action gaps can get really small. So these are the different colors or different discount factors. In the logarithmic space, you have a constant action gap of 2. And the other thing to note out is that the optimal policy remains the same. So if you look at So if it is above 0, going to the left is optimal, otherwise going to the right is optimal. So note I have a task where one is a reward of 1, the other one is 0.5. So like depending on where you are, you want to go one direction or the other direction. But the thing to point out is that the correspondences where they cut the line is exactly the same. So your optimal policy is not affected, but just your action gaps are affected. Okay, so just to show you what that does there is this a little thing that you still want to represent values of zeros, but with a logarithm you can't do that, so you have to add this little value there, and so k becomes a hyperparameter, and depending on the hyperparameter, you want to set it right to make sure your action gap deviation is small. So the blue line here is the original one that sort of goes up. If you set your k right, it sort of goes down, stays very close to 0 for all your discount vectors. Okay, now this is just deterministic case, positive rewards. Now it took us a long time to generalize this to the general case of general rewards as well as stochastic environments. Now I already thought I don't have time to explain this, and I would love to, but you'll have to read the paper. So I'm just going to tell you it's a miracle, and but it actually works. So I just want to look at the results of that algorithm. So we generalized this logarithmic Q-learning method to the to the case where we can apply it to here. So I just want to show you this is the Q-learning results where we had that very bad drop-off, and if we apply logarithmic Q-learning, again same settings, linear function approximation, different widths, we're seeing the following. This is the final performance, but also the early performance confirms that we now have good performance across our whole range. So this sort of validates that theorem. We had to do a lot of work to come up with a method that we could actually test it, but now this validates it, and as a side product it gives us a cool method that we can now use. Yes?
Does your final performance depend on the new hyperparameter that you introduced, or is it insensitive?
So it does depend on this hyperparameter. But there is sort of pretty rules of thumbs to set it easily. So we used a fixed value. So we just set the trick is you have to set it for 50 states. So it depends on the size of depends on the sparsity of your reward. So you want to set it higher than 50. That's a trick, but not much higher. So I think we set it to 100 here, and then you get this performance. Okay. Now, of course, this is nice for understanding. We applied it to a deep learning setting as well. So this is Atari DQN. We did the same things, and this is sort of what we saw. So yellow just means that you have a significant performance difference of over 50%. And so we do on a whole lot. We do on a few games worse. On a lot we do better as well. Overall, a positive improvement. But you might wonder what discount factor did we use here. So we used here, we scanned over a range pretty close to the high value. So the discount factor ultimately we used was 0.96. We did a scan of obviously for DQN as well as logarithmic DQN. And so logarithmic DQN, the optimal value was actually the default setting, which is 0.99. Like in Atari, 0.9 is not always the best choice. With linear function approximation, I would agree, by the way. But with, if you, so 0.99, we use 0.96. So that sort of concludes the talk. I just want to say give a few final remarks. So just to give a summary of the talk. So we defined the metro gap and showed that for some tasks, the metro gap is smaller when you have low discount factors. Then it showed that on sparse reward domains, low discount factors combined with function approximation perform very poorly in practice using current methods. And we hypothesized that this is related to the size difference of action gaps across the state space. And then we constructed a method, logarithmic Q-learning, that can reduce the size difference substantially. And we then validated our hypothesis, demonstrating that our new method achieves strong performance across all discount factors on this chain task. So what are some of the open issues? Now, first one is try different logarithmic mapping functions. So you can ask yourself, why do these perform poorly? Well, so the reason is that we optimize, like the method we designed, the mapping function we designed was designed for sparse reward domains, and not all these domains are sparse reward domains. If you look at skiing, for example, you get a -1 reward at every time step, and so it's super non-sparse. Now, we believe we can still do very well on this task, but we have to use a different logarithmic mapping function. So that's another, like, what kind of mapping function should we use to do well on these type of tasks? That is one of the questions. And the other question is, and that is, yeah, sort of, like, we used a value of 0.96 here. That is not very, I wouldn't call that very low yet. So we tried values of 0.1 as well on some of the games, and that didn't perform as well as I had anticipated. And I think it can be resolved, and I want to resolve it. So that's what I'm. So we in linear function approximation, it works very well. We can construct any task. It's going to do very well for low discount factors. Just in the deep learning setting, there's all these other hyperparameters, and so we assume what we think is that, you know, they are sort of optimized for these very high discount factors, but they don't necessarily transfer over to these very low regions. So we want to play a little bit more and see, okay, what type of things affect it, like, yeah. So for example, also the scaling factor I had in my mapping function, a vector c with scales values. That shouldn't matter for your learning, and in the linear case, it doesn't. All of a sudden, in deep learning, it matters a lot. You know, a parameter that is irrelevant in linear function approximation, all of a sudden you have to sort of tune it in the deep learning setting. I have a lot of frustration about that, and so my next paper might be trying to do something about that. Yeah, so these are the two things that are open issues next work. I want to finally, a small plug. Well, I'm from Microsoft Research in Montreal. We do lots of cool research like this and others on reinforcement learning and other things. If you like to, well, if you're in the neighborhood, drop by. If you like to do an internship or something, we have lots of great positions, so you can send me an email if you like. Right, that's it. Yes. Questions?
Why can't we minimize the finite horizon objective? Why do we have to come up with a discount?
Well, that's a very good question. So, like, one of the reasons is that if you have a finite objective, finite undiscounted objective, your policy can be non-stationary, and which complicates the learning methods considerably. So, the fact that you can search among the stationary policies, if you use an infinite discounted objective, gives you huge benefits. And so, more generally, like, what you want to, the way you want to evaluate your agent ultimately is not always the best way, the easiest way to improve your, like, to optimize on. So it can just, because, you know, there is this balance between final performance and sort of speed of learning. And, you know, there is, like in this work, but also in other work, there's a lot of evidence for that. Yeah, it might be very advantageous to sometimes use a learning metric that is easier to optimize on for the agents.
Well, the question, would we have the same problem if we make time step part of our feature state representation?
No, but then you have a different problem, which is that your state space explodes. So you're just trading, you're trading one hard problem for a different hard problem. So I feel I should ask the question again, like, who if we have a sparse reward problem, function approximation, who thinks we should use high discount factors?
Gamma 1 forever.
All right, but use reduction, I see that as a success. That's great.
So is your end goal to get the gamma zeros?
No. So it's really. So it really depends, right? So I show those different tasks where for some tasks high distance factors are better, for others low are better. So what I really want to do is enable that whole range, and so that you can play with the whole range and see what works well. Now the case is, well, you can play with it, but due to sort of optimization peculiarities, you can't really optimize over the whole range because you're restricted to these very high discount factors, because otherwise your performance falls flat. With this method, you can actually play with it. It's not going to help on all problems, because on some problems just work better with high discount factors, as I showed examples of. But now, if you come across a problem where, where you really want to use smaller discount factor, you now have that opportunity. Oh yeah, and one other thing I want to mention is like how this research got started is that like we did some work on Atari, Miss Pac-Man, and what we saw there is that we were using high discount factors, and we tried to get as good behavior as possible. And what we saw is that, well, you have all these pellets that an agent needs to eat, and what we sometimes saw by watching runs is that sometimes it seemed to ignore a pellet that was just next to it, while it went for a number of pellets, a group of pellets that was farther away. And initially we thought, okay, this is just some approximation error. But when I went deeper into it, I found out it's actually not an error. This is its optimal policy. So its optimal policy is to disregard the pellet that is just next to it and go for these others. Where the goal of the game is you have to get all of them. So it seems like a very, from what you really want to optimize on, it's not a good move. So that's sort of how the seed of this work started, like thinking about that, and that led to this ultimately. So it's actually a real, it's not a, yeah, it's a real thing that sometimes you actually do want to use smaller discount factors. So I'm solving a different equation than my performance metric. So like if you would compute, yeah, so it's a different, you know, it has a discount factor, for example. Whereas the assumption here was that I had a performance metric. So, like the main underlying statement here is that the way you evaluate it is different than what you tell your agent to optimize on, and you can and the reason is that you want to do that is that it can be very hard on what you really care about. If it's a really sparse reward problem, for example, maybe you want to add some extra rewards just to make the problem easier. And so fundamentally, yeah, computing the optimal policy for your performance metric is going to be different, could be different, will be different in general than your optimal policy under your learning metric. So, you know, and those there's all kinds of situations, like different performance metrics you could define. Specifically, I focused on a common one of Atari, also because I ran into the problem in an Atari setting, so I wanted to solve that. But yeah, you can play with different types of metrics, but the same problem exists. Like you're always going to have a metric gap, and it's going to depend on your hyperparameters. So then you can ask yourself, okay, what are good hyperparameters to actually do well on this thing, that the performance metrics that I really care about. Any more questions? Yes, Rich.
So there's this thing where you have the two metrics. Do you think it's possible that that's a mistake to have two? That the answer could be that we should only have one?
So I don't think it's a mistake. I think it's actually it's from, if you look from a pure perspective, you maybe only want to optimize on what you really care about. But from a more practical perspective, it can be like if your reward function is super sparse, you like it's not good as a learning signal. So in that case, having separate metrics can really help. Plus, in addition to that, I think you can still, if you care about not wanting to provide any bias, you could still consider a setting where you would learn that bias, where you would learn, you can think of an evolutionary process on top of what I showed that tries out different learning metrics until it finds one that is sort of corresponds well with this performance metric. Maybe it's sort of related to dying or not, but you can't optimize for dying because that's too sparse. So maybe evolutionary, it tries different learning metrics, like some where the agent just explores, you just try things. Some where it really wants to learn, and some of those metrics are going to be well correlated, or have a good are good in correspondence with this true metric. But I do believe that it can be very beneficial. It's a strategy that can be very beneficial.
And I have a question about the lab, the Microsoft lab.
Sure, yeah.
Do you think we could have a Microsoft lab here in Edmonton?
I would like that. I would like that.
Cool.
Yeah.
Why not?
Yeah. Well, yeah.
Did you see?
Like I can't make that decision. Obviously, you wouldn't have to talk to me, but maybe if you send an email to Satya, and he might think about it.
Okay, let's work on that. Thank you very much, Harlan.
Right.